this video, we will learn to apply the principles of dynamics to solve problems involving rectilinear motion with no acceleration, rectilinear motion with constant acceleration, and free-falling bodies. When we require only one coordinate axis along with time to describe the motion of a particle, it is said to be in linear motion or rectilinear motion. Some examples of linear motion are a parade of soldiers, a train moving along a straight path, and many more. Consider a flat body. When the resultant of external forces that act on the body is passing through the center of gravity of the body being considered, the path of motion will be passing along the center of gravity, collinear with the line of action of the resultant force. In this case, there is no rotation. Remember that the direction of the resultant external force will dictate the direction of motion. And if the direction of the resultant force is constant, the motion path of all particles will be straight lines parallel with each other, and this is called rectilinear translation. The use of elevators in public places is an example of rectilinear motion. This is happening along the vertical axis. Gravitational forces acting on objects resulting in freefall is an example of rectilinear motion also. That is also happening on the vertical axis. Kids sliding down on a slide is a rectilinear motion. In this case, the line of the path of motion is parallel with the surface of the slide. There are basically three types of rectilinear motion: uniform rectilinear motion, uniformly accelerated rectilinear motion, and rectilinear movement with non-uniform acceleration. When an object travels at a constant speed with zero acceleration, it is known as uniform rectilinear motion. When an object travels with constant acceleration, it is known as uniformly accelerated rectilinear motion, or there is constant change in its speed. When an object travels with an irregular speed and acceleration, it is known as rectilinear movement with non-uniform acceleration. Uniform rectilinear motion is also called motion with no acceleration or zero acceleration. It happens when the initial velocity is equal to the final velocity at any given time. Consider a biker that rides his bike and its direction of motion is going to the right. It will have its initial velocity equal to 5 meters per second, and the acceleration is equal to 0 meters per second squared, which makes sense because there is no acceleration for these types of motion, uniform rectilinear motion. After a time interval of 1 second, it has traveled 5 meters. Its final velocity at the end of this time interval is equal to 5 meters per second because there is no change in the speed of the bicycle. After another second, it also traveled another 5 meters and another 5 meters and another 5 meters. Its final velocity will always be equal to its initial velocity. This is the case for uniform rectilinear motion or motion with no acceleration, traveling equal distances at equal time intervals. For motions with no acceleration, the equation of motion for mathematical computations would be velocity final is equal to the initial velocity. The average velocity or simply velocity is equal to s over t. A is equal to the acceleration and that is equal to 0. T is equal to the time elapsed or time interval, and s is equal to the distance or displacement that you are considering. So let's have an example of a uniform rectilinear motion. We have here problem: a car traveled 10 kilometers without changing its velocity of 20 kph. This is kilometer per hour. How long was his travel time? So just like in any problem solving, the first step is always to write the given values. So the given values are the distance that he traveled. So he traveled a distance of 10 kilometers. This is kilometers. And his velocity is equal to 20 kilometers per hour. We have a condition here. The car did not change its velocity, meaning the acceleration is equal to 0. Okay. So this is initial velocity equal to final velocity. Okay, we are looking for the travel time or the time interval. That is our required value. We are looking for the time. Let's try to draw it for visualization. So we have the car starting point, and this is the final point or final position of the car. So this is the total distance that he traveled. Let's say this is D, that is equal to 10 kilometers. And its initial velocity is equal to 20 kph. And that is still his final velocity. 20 kph. The acceleration is equal to 0. So to solve for this one, we are looking for the travel time, the average velocity. This is simply equal to V. Is just equal to the distance traveled. This can also be written as S. So this is S over T, the distance traveled over the time interval that we are considering. So we are looking for the time interval. So let's manipulate the equation. This will be written as T is equal to S over V. So for the time interval, this is 10 kilometers divided by the velocity equal to 20 kilometers per hour. This will cancel and R will transfer at the numerator. So the time interval is just equal to 0.5 hours or 30 minutes. The uniformly accelerated rectilinear motion is the type of motion wherein the final velocity is greater than the initial velocity, and there is an equal increase for velocity considering the same time interval. Consider this biker, and its direction of motion is again going to the right. It will have an initial velocity of 5 meters per second, and the acceleration now will be positive 3 meters per second squared. After 1 second, the biker has traveled 6.5 meters. And by that time, at the end of this interval, its final velocity is equal to 8 meters per second. Notice that we have added 3 meters from its initial velocity because the initial velocity is 5 and the acceleration is 3. We are adding 3 meters per second every second. So after another second, it has traveled 9.5 meters. And its final velocity by that time is now 11 meters per second. Again, we added 3 meters per second. And then after another second, it has traveled 12.5 meters with the same time interval of 1 second. And its final velocity at the end of this interval is now 14 meters per second. Again, we added 3 meters per second because the acceleration is 3 meters per second squared. or 3 meters per second per second. This is uniformly accelerated rectilinear motion. If uniformly accelerated rectilinear motion considers equal increase for velocity considering the same time interval, uniformly decelerated rectilinear motion is just the opposite of it, wherein the initial velocity is greater than the final velocity, and there is equal decrease for velocity considering the same time interval. If you will consider the same bicycle and it will have its direction of motion going to the right, its initial velocity is 14 meters per second with an acceleration or deceleration in this case because it is a negative value. Acceleration is equal to negative 3 meters per second squared. So, after 1 second, it has traveled 12.5 meters. And its final velocity at the end of this interval is now 11 meters per second. After another second, it traveled 9.5 meters, and its final velocity at the end of this interval is 8 meters per second. After another second of time interval, its final velocity will become 5 meters per second. So basically, uniformly accelerated or decelerated rectilinear motion considers the same concept. It is equal increase or decrease of velocity considering the same time interval. The value of the acceleration dictates whether it is accelerating or decelerating. Accelerating means increase for velocity, while deceleration means decrease for velocity. For motions with constant acceleration, or uniformly accelerated or decelerated rectilinear motion, the following kinematic equations of motions are going to be used. Again, we have your initial velocity, final velocity, average velocity. A is the acceleration or deceleration. If that is acceleration, that would have a positive value. And if that is deceleration, it would have its negative value. T is the time elapsed or time interval that you are considering. X is the distance or displacement of the object at the end of the time interval. And X sub 0 or X sub O is just the initial position of the object that we are considering prior to its start of motion. Now let's have an example for uniformly accelerated rectilinear motion. We have here a problem. An airplane accelerates down a runway at 3.2 meter per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. I have written down the given values. You have an acceleration of 3.2 meters per second. That's why it's positive. That is acceleration. The time interval before its takeoff from its starting position is 32.8 seconds. We are looking for the distance that it has traveled before it finally take off from the ground. Okay, this is our drawing for visualization. So this is the distance that we are looking for. X, or the displacement. The time is 32.8 and acceleration is 3.2 meters per second squared. Naturally, we will ask, what is its initial velocity? Now, common sense will dictate that it started from rest. A car should always start from rest. If it is not given, if the initial velocity is not given, so you should assume that it is equal to 0 meters per second. And the final velocity, or the velocity just before it takes off, is unknown. Now for these types of problems, it is advisable to look for the equation with the least unknown values to save time from our kinematic equations of motions for motions with constant acceleration, or what we call as uniformly accelerated rectilinear motion, we have basically four equations that we can use. And if you will look for the equation with the least unknown values, it is the second equation here, written as x is equal to x sub o plus initial velocity times time plus 1/2 acceleration times time squared. Now what is x sub 0? That is describing the initial position of our object. So if you will if you will imagine that this is a number line, for example, this is a number line, this is our x sub 0. We reference it at the starting point. So let's just say that it is equal to 0. So this is just 0. And x is equal to this value from the reference point of 0 in the number line. So we are looking for the value of x, initial velocity of 0 meters per second. So any value that you multiplied by 0 will just be equal to 0. So we are left with this equation. X is equal to 1/2 of the acceleration times time squared. And since this is the equation, we don't need to find the value of the final velocity right before it took off. So we can immediately solve this. This is 1/2 of acceleration is 3.2 meter per second squared, and the time is 32.8 seconds. Let me transfer this one here. X is equal to 1/2 3.2 meters per second squared. The time is 32.8 seconds. The quantity is squared. So for the units, second squared will just cancel with this unit second. If you square that, it will be second squared per second squared, so it will cancel, leaving us with the unit in meters. So the distance traveled before it took off is 1/2 times 3.2 times 32.8. Don't forget that it is squared. 1721.344 meters. We have your answer for the problem. Uniformly accelerated or decelerated rectilinear motion is usually considered for objects that are moving along the horizontal axis, while free-falling bodies is similar to these concepts, but in this case we are considering objects that are moving along the vertical axis. Free-falling bodies are influenced by the Earth's gravitational attraction, and it uses the same equations of objects in uniformly accelerated and decelerated motion. The velocity of the object when it will reach its maximum height is 0. So for it to be launched going up, it should have an initial velocity that is not equal to 0, because if that is equal to 0, then there will be no height y, or it will not be launched. So initial velocity when it's going up should always have a value, and when it will reach its maximum height, the velocity at that time is 0. So from a higher velocity to a velocity equal to 0, meaning we are decelerating. When it will fall from the maximum height, it will have an initial velocity by that time equal to 0. And when it falls back to the ground, or to any time interval that we are considering, When it falls down, it will accelerate by that time. So the acceleration is always due to gravity, acceleration or deceleration. When the object is going up, we are considering deceleration because it is decreasing its velocity. When it is going down, or when the object is being dropped, then we are considering acceleration. So the value of the acceleration due to gravity is equal to 9.81 meters per second squared, or 981 centimeters per second squared, or 32.2 feet per second squared. If the object moves, with the force of gravity, or it is falling, we use positive g because that is accelerating. Otherwise, if it is going up, we use the negative value of the acceleration due to gravity, which is g. For free-falling bodies, we will use the following kinematic equations of motion. If you will notice, these are very similar to uniformly accelerated or decelerated rectilinear motion. It is just, instead of using x to designate the value for the distance, we will now use y because we are considering it in the vertical axis. So let's have an example for free-falling bodies. An apple was dropped into a deep well. After 3 seconds, it was heard to hit the water surface. Determine the depth of the water surface. I have written down the given values. Since this is a free-falling body, its acceleration is due to gravity, and that is equal to 9.81 meter per second squared. The time interval from its initial to its final position at the water surface is 3 seconds. We are asked to determine the depth of the water surface. Now I have drawn the figure. It was dropped with this reference point. Let's name this y sub 0. And if you will assume that this is a vertical coordinate axis, we can say that this point here is negative y, that is below the origin of our axis. So let's say it's negative, just for the sake of designating the direction of our position. So similar with uniformly accelerated rectilinear motion, we will look for the equation with the least unknown values to save our time. This is simply equal to y, or negative y for the direction, and we are given the acceleration due to gravity and the time interval. Its initial position or initial velocity, since that is free-falling bodies, it is not acted upon by external forces that will cause its initial velocity to be greater than 1, because that is just dropped. It is dropped into a deep well. So the initial velocity v sub I is equal to 0 meter per second. And since it is acting on the direction of the gravitational force, it will have its final velocity when it will hit the surface of the water, and that is also unknown. We can use this formula: y is equal to y sub o plus initial velocity times time plus 1/2 of acceleration due to gravity times the time squared. Since our initial velocity is equal to 0, even if any number that we multiply by 0 will just be equal to 0, so we can cancel that one. Let's reference this as our initial position. Let's just say that this is 0. Let's write negative here so that we can designate it to be below the initial position, just for the direction. So we have y is equal to negative 1/2. Gravitational acceleration is equal to 9.81 meters per second squared. And the time interval is 3 seconds. The quantities is squared. So second squared divided by second squared will cancel out, leaving us with a unit of meters. So this would be 1/2 times 9.81. This should be 9.81 times 3 squared. The depth of the water is equal to negative 44.145 meters. Your negative is just considering the direction, meaning it is below the reference point or reference or initial position of the object. So that is how you solve free-falling bodies. They are very similar with uniformly accelerated or decelerated rectilinear motion. As a recall, we have learned that acceleration is the rate of change of velocity with respect to time. Increasing change in velocity is positive, while decreasing change in velocity is negative. Also, acceleration for free-falling bodies is due to gravity or gravitational acceleration. Motion with the direction of gravitational force uses positive g. Remember that the gravitational force is always going down, pulling objects to the center of the earth, while motion against the direction of gravitational force uses negative g. Thanks for watching. If you like this video, don't forget to hit the like and subscribe button and turn on the notification bell.